Good morning, everybody, and welcome to today's webinar. The webinar is organised and hosted by 3 EC-funded projects: WENDY, WIMBY, and JustWind4All. Our topic is wind energy and how we can understand the impact of wind farms and the energy that they create. I know that we have around 50 registrants today, so just as people start to join the webinar, I'll just give a brief introduction to today's event. My name is Nick Ferguson, and I'm a senior manager at Trust IT, and we're one of the organisations which run and deliver services for the Horizon Results Booster, which supports projects to collaborate on joint dissemination activities, and it provides also support to EC-funded projects on exploitation activities. A new Horizon Results Booster service will start in November, and we're very excited and looking forward to supporting projects for another 4 years around dissemination and exploitation. So let's get down to business with today's webinar. So, wind energy and wind farms are one of the fastest growing energy and renewable energy sources in Europe today. The cost of creating wind turbines are coming down, and the capacity of for them to create energy is increasing too. And it now provides over 1/3 of total electricity generated from renewable sources in Europe in 2022. Wind farms and renewable energy also have created over 300,000 jobs as well in Europe, and this number, objectives around this number are due to increase up to almost 1 million in the next few years. However, despite this, there's also community resistance to wind farms and their installation. Many groups, as you can see, the people on the left protest against the impact that wind farms have on their local communities. They complain about the noise, shadow flickers, and health issues as well associated with their implementation. And the whole concept of NIMBY, so not in my backyard, has emerged as communities, although they see the benefit of wind energy and renewable energy on climate and the environment, they're not so keen on having these installations in their backyard, in their communities. So how can you address this, and how can communities be brought in so that they want these installations in their community? Well, there's a lot of work being done in this area, and today's projects will look at different ways in which they can share and educate and involve communities on the impact that renewable energies can have, not only on a national or European level, but also on their own communities too. In fact, you can see on the right, the second photo, a group of people. Again, both photos are in Ireland, and the second group is a community group who have launched their own wind farm. So let's get down to business. We have 4 exciting presentations. I'll be introducing Jan Wijnand from the Institute of Jülich Systems Analysis in just a moment, and he'll be giving our keynote presentation. And then we'll hear from each of the 3 projects, Just4Wind, WENDY, and WIMBY, who will be talking and showing us their various solutions. There'll be time at the end for questions, and I'd kindly ask people to put their questions in the Q&A so that the speakers can see them, and we'll come to those when we get to the end of the presentations. So with that, I'd like to hand over to Jan, who will give the first presentation. Jan is head of Integrated Scenarios Department at the Jülich Systems Analysis Institute, and he coordinates around 30 scientists and PhD students. So Jan, I'll stop sharing my slides and you can share yours. So over to you. Thank you.
Yeah, thanks a lot, Nicholas, for the kind introduction. I hope you can see my slides now as well. I mean, you saw the title. Yes. Yeah, perfect. You saw the title already in Nicholas' slides on integrative analysis of wind farm impacts, a holistic approach with social, environmental, and technical challenges. But today in my talk, I will focus on the social challenges. And before I start, maybe a quick introduction of myself. As Nicholas said, I'm department leader at the Research Center Jülich at the Institute Jülich Systems Analysis. And my department develops applications for the holistically optimized design and transformation of energy systems. And you can see also our doctoral researcher, Samara Zani here. I show her here because most of the credit of these studies I show you goes to her. She was the first author. And yeah, with this, I would like to start. I will show you an example of how you could try to integrate social factors in renewable energy planning models, because we realized that our techno-economic models often overestimate the actual feasible potential of renewable energy. And because in reality, as we learned also from Nicholas' presentations, many renewable projects got delayed or cancelled due to local opposition, and therefore it's important that the public concerns are also considered early in the planning stage. But the challenges are that there's no agreement on the definition or relevance of specific social factors at the moment, and it's often difficult to quantify them on a large scale because they are also subject to local characteristics. So our research questions that we tried to answer were, how can we quantify these social factors and integrate them in energy system planning models? And then if we do that, what would be the impacts on the remaining renewable potentials, optimized system costs, and energy system transformation pathways? We started with a systematic literature review and identified that most of the studies who tried to quantify social factors for onshore wind farm planning were case studies in European or North American countries. And you can see here the social factors that were quantified in the studies. We clustered them here in different groups. And we identified that visual impacts or proximity to turbines were the most used factors. And in fact, visual impacts is one of the most important factors for local acceptance. The studies often try to quantify these social factors by modeling them in land eligibility analyses, in multi-criteria assessments or welfare analyses. But there's also a lack of longitudinal and cross-cultural studies in the literature. And we also saw an increase in justice considerations, but there's also a lack of conceptual and empirical foundations. And what I want to show you now is, based on the literature review, how we try to incorporate visual landscape concerns in quantitative energy system planning. So conventional visual impact assessments with viewshed analyses are usually done after site selection, which means that a turbine or wind farm is installed and then it's examined how far this wind farm or turbine can be seen. But there's also a new method coming up, which is called reverse viewshed method, which enables an a priori integration of visual impacts considerations. And I will explain this method on one of the following slides. But there was no study yet on a large scale or which even integrated these viewshed maps in energy system optimization models. So our goal was the design of renewable energy systems with low visual landscape impacts at a national level and to analyze the implications on the optimized system costs and energy transformation pathways. We used Germany as a case study because for Germany, we had data on a 1 by 1 kilometer square grid on scenicness and also on population density data. You can see here in the map the scenicness data. The darker the purple is, the higher the scenicness is, which means that the landscapes are very attractive. With a scenicness rating of 1, they have a low scenicness, and with 9, they have a high scenicness. And then we performed reverse viewshed analyses for different scenarios. So for scenicness, from scenicness greater or equal to 9 down to greater or equal to 5. And this latter scenario combines all the scenicness levels above. So it gets stricter with lower scenicness here. And we did the same for population density from equal or greater than 5,000 people per kilometer square to greater or equal to 300. And then we used the reverse viewshed maps as exclusion zones in our land eligibility and potential analysis for renewable energy plants, where we placed wind turbines and also PV panels and simulated the electricity generation. This was again input then for our techno-economic analysis, where we optimized the cost optimal greenhouse gas neutral energy system of Germany by 2045 with wind turbines and PV modules under different visibility scenarios. Just to explain you how this reverse viewshed analysis works, you have a viewpoint. In our case, these were about 370,000 viewpoints in Germany. With this high number, it gets quite complex because you use then digital elevation models to calculate how far you can see from this viewpoint. Based on visibility thresholds, which are 7.5 kilometers for PV modules and 11 kilometers for wind turbines. And then you can see that in this case, for example, a few wind turbines are partly visible, others are fully visible, and then there are also some which are not visible either because of the elevation or because of the visibility threshold, that you do not see them anymore or good enough. Just to give you an example, what the result would be, I show this here for a small case study. So a district of Aachen, a small district in Germany. You can see our base scenario here where no viewsheds were taken into account. So here in green, you see eligible areas to install wind turbines. This is based on conventional criteria like setback distances to settlements, or also technical restrictions like the elevation. And then for different scenarios, we combined this with the reverse viewshed maps. In this case here, we used the centroids with scenicness, with landscapes with scenicness equal to 9. And then you can see the resulting reverse viewshed maps, and the turbines you could see here on the bottom of this district are now excluded. The same here with population density, with the city of Aachen and the visibility from there. Yeah, this is now a result for the whole of Germany. The base scenario has no viewsheds, and here you can see combined viewsheds from scenicness 9 to scenicness greater or equal to 5. So from left to right, there's a higher sensitivity to visual impacts. In the first row, you see it for wind turbines. In the second row, for open field PV modules. And in this diagram on the bottom of the slide, you can see the capacity potential of the different technologies and the population which will not see any renewable energy plants in this scenario. And you can see, as you would expect, with the stricter visibility scenario, the capacities decrease. Onshore wind, there's nearly no onshore wind potential left for the strictest scenario. And but you also see that offshore wind capacity doesn't change. This is because in Germany we have a minimum distance, I think, of 16 kilometers from the coast, which is higher than the visibility threshold for this technology. And 25% of the people living in Germany wouldn't see any renewable energy plants in this scenario. Yeah, here you can also see it for the population density scenarios. The outcome is nearly the same. The reverse viewsheds are different locations, but the capacities decrease again. But in this case, as you might expect, because it's based on population data, the population which would not see any onshore wind turbines or open field PV panels is much higher in the strictest scenario, with 87% of the German population. Here you can see now the cumulative generation potential of the technologies, and on the y-axis the levelized cost of electricity. So how much euro would it cost to provide 1 megawatt hour of electricity? In the first row for onshore wind, in the second row for open field PV. You can see here this area in light purple, which represents the current generation in Germany. Then in light green, the 2030 target, and in dark green, the 2040 target. And as you can see, for wind, there's almost no potential left if the sensitivity to visual impacts is set to the strictest scenario. So also 2030 and 40 targets cannot be achieved. For PV, it looks similar, but there's still more potential left. And so open field PV together with rooftop PV could mean that in these stricter scenarios, the technologies might shift more to PV from wind. And yeah, now I show you the impacts on costs and the system composition for the strictest scenarios. So scenario with thickness greater or equal to 5, or population density greater or equal to 300 people per kilometer square. And in the first row, you see the relative deviation of cost from the baseline scenario, so the scenario without any viewsheds or visibility considered. And on the bottom, it's the deviation of the electricity supply and the hydrogen import share. You can see clearly in the top diagrams that the largest deviation is in the energy sector. So this would mean the supply technologies. And here we have an increase of 38% by 2000 in costs by 2045. And when you look at the system composition, so which technologies are chosen for the cost optimal system, you see a massive reduction in onshore wind capacities and also open field PV. And this shift or substituted by rooftop PV in yellow and offshore wind. And the hydrogen import share is shown here with this blue line. And this also increases in these scenarios, which means that Germany would be much more dependent on other countries to import hydrogen. Now to summarize all results, you can see here again annual system costs by 2045 in billion euros over the different scenarios, starting with the base scenario, and then the scenarios are ordered by the change in system costs. And you can see here, if you only moderately minimize visual landscape impacts, so up to the scenario population density greater or equal to 3,500 people, there's almost no change in annual system costs. So these scenarios are not financially binding. But then the preferences from onshore wind go to open field PV, and the costs increase up to 9 or 11% in 2045. and also the share of rooftop PV and offshore wind is increasing here. And from this point onwards, we also utilize all offshore wind potentials in Germany. In the red area here, we also utilize all rooftop PV potentials, which is very uncertain that this is possible, and probably also introduces new social opposition. The hydrogen share is increasing, as I showed, and we also use more fossil fuels in the early transformation years. So this strategy will reduce the resiliency of the German energy system by forcing the system to heavily rely on rooftop PV adoption and high share of hydrogen imports. So with these results, we hope that policymakers can use them for their decision making. If we should put more importance to visibility of renewable plants or costs or other factors. Yeah, so much from my side. Yeah, I'm looking forward to the questions that you have in the later Q&A session, and also to the other presentations by the other colleagues. Thank you for your attention.
Thank you very much, Jan. That's really interesting, and you know the importance of having policymakers make their decisions based on evidence and statistics and data is very important. So I'm sure your study with your colleagues is vital for that. So thank you, Jan. If you have any, well, please do post questions. You know, we have the time at the end for you to put your questions to the speakers. So please put them in the Q&A, and we can come to them later. So put them in now before you forget. Okay, so let's move on now. Thank you, Jan. And if I can ask Miguel to put his camera on and share his screen. So apologies first for my pronunciation. Miguel Sierra y Montoya, which is a Catalan name, I was told before this, is from the Universitat Autónoma de Barcelona. And he's, of course, is representing the JustWind4All project. So Miguel, over to you. Thank you.
Thanks, Nick, for the introduction. And indeed, it was very well pronunciation, so good. So hi, everyone. Thank you for making it to this webinar. I'm Miguel from the JustWind4All project, and I'll be explaining a bit our approach to the holistic impact assessment. So first, briefly, an introduction of what the JustWind4All project is about. So the idea is, the main goal is to support the acceleration of on and offshore wind, but with focus on justice and governance. And for this, we identified 4 key challenges to address, and these relate to knowledge, justice, policy frameworks, and also novel resources. And here in novel resources, we would include, for example, new practices just as repowering, but also novel technologies like airborne wind. And the framework of the project to tackle complex problems such as integrating more wind energy into the system is, first we define the problems, and these relate to the 4 challenges. Then we collect data and insights using several tools like life cycle assessment or energy system modeling, as I will explain later. And then we try to co-produce, validate, and implement using these methods some analysis with stakeholders. And for this, we have a wind forum and several wind labs to test what comes out of the analysis and make it fit for purpose. So in this presentation, I'll be talking about the holistic impact assessment. And we have 4 tasks in this holistic impact assessment. The first one is to build a technical database that can help to do energy modeling and impact assessment. The second and third tasks relate to creating new metrics to assess holistic impact. and to develop EnBIOS, which is the main tool that we use in the project, and I'll explain what it is later. And then to create fit for purpose outputs, so the results that we get make sense and are useful for the different stakeholders. And in this presentation, I will go through each of these tasks and briefly explain to you how we are tackling them and what they did so far. So for the first task, the main tool that we are using is lifecycle assessment. And just in case you are not familiar with how it works, I'll briefly explain the basics. So in lifecycle assessment, you first start with an inventory. And in this inventory, you need to collect all the materials, land, water, and energy required to build a product, in this case, a wind turbine, but also the emissions and waste. And it is very important that you include all the life cycle stages of the product, so from the material extraction until the end of life. Then you have several life cycle impact assessment methods, and these are a series of indicators that are able to classify these emissions and extractions and then rate how harmful they can be to each of these indicators. So after we combine life cycle inventories and impact assessment methods, we come with some results. So for example, we could say that the climatic change impacts can be 100 tons of CO2 equivalents. And what is the problem in the moment with life cycle inventories of wind energy? In life cycle assessment, we mainly rely on one big database of life cycle inventories, and this is called EcoInvent. And there you only have very outdated data on wind turbines. So as you can see here, it's data from the 2000s. So it's not very representative of the kind of turbine that we have out there today or that we will have in the coming years. And also the powers might be small compared to the trends that we have at the moment. For example, the biggest onshore turbine is 4.5 megawatts in EcoInvent, but the biggest offshore is only 2 megawatts. And as you know, some of the manufacturers out there have announced like crazily big turbines. The Chinese have announced even up to 22 megawatt turbines, but in Europe we are about 15 megawatt turbines or offshore and around 7 point something megawatts onshore. So we need to make sure that the inventories that we use have new data and that they are able to represent big turbines as the ones that are being implemented and will be implemented in the future. So to overcome this issue, we came up with a tool called WindTrace that we developed within the project. And it is a life cycle inventory parametric model for wind turbines. And the way it works is that you can define several parameters. So you can say, okay, my turbine has this power, the half height is this rotor diameter. You can specify the manufacturer and the commissioning year of the turbine. And then combining all these parameters with technical data that is in the background of the model and that was taken from industry reports and literature, our tool is able to create life cycle inventories that represent well the turbine that you want to model. And we can give results at the turbine level, so we can model one single turbine, but we can also represent a wind park that would include several turbines, the cables between the turbines and the transformers. And we can have inventories at the unit level, so one turbine, but also inventories per kilowatt hour of electricity produced by these turbines. And later with these inventories, we can use the life cycle impact assessment methods that I mentioned before to know the impacts of building and installing these turbines. And we can also use these inventories in EnBIOS, which is our tool. So far in the project, we've developed this model to represent onshore turbines, but also to deal with different end-of-life strategies, including repowering, lifetime extension. Now we are working on offshore wind, and there we want to model floating platforms too. And unfortunately, we won't be able to include airborne wind in this model, but we are working in collaboration with Airborne Wind Europe to get some inventories from their side. And just in case you've never heard of Airborne and you're curious to know more, I encourage you a lot to get in touch with Airborne Wind Europe, because they can explain you better how this technology can play a key role in the future. So what this tool, our goal is to populate a database of wind turbines in Europe, but for each of these applications, onshore, repowering, and offshore, we did several things. For example, for onshore, we have been studying the influence on these technical parameters in the environmental impacts. In the repowering case, we are working on a case study with a real farm in Portugal, where they have different possible strategies to deal with the end of life, and we are trying to assess the impacts of each of these strategies. And for the offshore, we've been discussing with stakeholders what should be included to model better these turbines. And now I'm going to explain a bit about this study of the technical parameters and how they influence the environmental impacts. So we recently sent a paper that tries to study these parameters and how they influence the climate change impacts. And in this figure, for example, you can see in the x-axis the power of a turbine, and in the y-axis the impacts per megawatt hour. And as you can see, the bigger the turbine, so if you go to the right of the figure, the impacts per megawatt are becoming smaller, and this is because the amount of materials that you need to add to increase the power of a turbine are less. So this suggests that it would be worth considering bigger turbines instead of smaller turbines in terms of climate change impact. We also analyzed the role of the capacity factor in impact results. And the capacity factor means that if you place a turbine in a place that has better wind resources, it will be able to produce more electricity. And of course, the more electricity you can produce, the less are the impacts per kilowatt hour produced. So in this figure, you have in the x-axis the capacity factor. So if you go to the right, you're producing more electricity. And in the y-axis, you have the emissions per kilowatt hour. And of course, if we are able to place our turbines in sites where there is more wind and there can be more capacity factor, of course, the emissions of the turbines will decrease. And finally, we also look at the steel production process. And this is important because if we have a look at the life cycle phase contribution of each of the phases of the turbine, the materials phase is the biggest one to almost all the impact categories that we analyzed, between 70 and 90-something%. And in particular, in the case of global warming, steel and chromium steel of the turbine made up almost to 50% of the total impacts of the turbine. So it makes sense to have a look at what happens if we are able to produce greener steel in the future, so the impact of our turbines can be reduced. And this is what we found out. Here you have an orange line in the middle that represents the amount of recycled steel that we have currently in Europe, and is about 43%. And the exercise that we did here is what happens if we are able to use more recycled steel and to use greener electricity mix to produce this steel. So the potential to reduce climate change impact of turbines is up to 28% if we were able to produce 100% recycled steel with the electricity mix of Norway that relies a lot on hydro power. In the second task, we try to develop new metrics, and these are based on social metabolism. And just to give you a taste of what social metabolism is, in social metabolism, we understand the economic system as something that consumes energy and materials, and these energy and materials are of high quality, and after the economic process, they get degraded into heat and degraded into waste. So it's very important to track all the energy and material flows through the economic process so we can understand what's going on. And to give you an example of how this looks to analyze one technology, this is a paper published in 2013 that tries to assess the nuclear energy, and what they do is to account for all the uranium that you need to operate a power plant, and then all the waste that you produced, and then of course you need to account for the constraints, like if you don't have enough uranium for all the plants that you are planning to construct, it doesn't make sense. So because you have a biophysical constraint, but also the environment has some sink capacity of processing waste. So this is also a constraint. And also all the materials, labor, and power capacity that you need to operate these systems are a constraint. So if you don't have enough labor or materials, you cannot build the infrastructure that will be able to supply this power. So this is the kind of social metabolism approach that we try to apply to wind energy now. And in this new holistic metrics, sorry. We focused on the wake effect so far for offshore wind. So when you place a turbine in the marine environment, when the wind reaches the turbine, behind the turbine, it gets turbulent and it loses speed. So this can influence a bit on the water mixing column, and the water mixing column is very important because it helps to mix the nutrients that then all the life in the ocean uses. So if we are affecting this water column mix, we might be having other effects on the ocean that it's important to understand. And to analyze this, we are working on a case study on a proposed wind park in Catalonia called Park Tramuntana, and we try to link ecosystem services with social metabolism. And this is the results of it. I won't go in deep into it, but the main idea is that we try to connect the economy, so the yellow part, at different levels, at the local level, regional level, and the global level. And we try to connect it with the ecosphere, what happens elsewhere, like outside of the economy, also at the global, regional, and local level. And we try to analyze the interactions between all these levels to understand what the cascading effects might be of this possible wake effect. Then the third task is to develop MBIOS, and MBIOS is the main tool that we use in the group. And what we try to do is to combine life cycle assessment with social metabolism. And it is a tool that is open source, and you can find it in GitHub if you want to have a look at it. And the main idea is that you can analyze the energy system at very different levels. So you can analyze them at the energy technology, like the impacts of wind in particular, or solar in particular, or at different levels up to the entire energy system. And what we do in MBIOS is to work in close collaboration in the project with the work package 2, and there they do energy system optimization model with a modeling tool called Calliope. And this model, what it does is to provide different energy system configurations in 2050 for Europe. And these are techno-economically feasible energy system configurations. So to put it very simple and simplify it like maybe too much, what Calliope would give is a possible distribution of wind turbines and solar photovoltaics, among other technologies that can fulfill the demands, and it provides different possible configurations to place the turbines here or there and increase the transmission lines to accommodate all of this. So what we are trying to work in is to combine Calliope, this energy system model, with EnBIOS and do something similar as what I'm presenting here. That was a work on another project in Portugal. And here what we did was each of the dots in this plot is a energy system configuration, and each of the columns is a different indicator, and the blue line is what we have at the moment, like a 2020 in Portugal. So all the results below the blue line are indicators that will be like sorry, are system configuration, energy system configurations that will be improving in 2050, but all the points above the blue line are indicators that will be worsening in the future. And of course, when you look at metal depletion, and this is the main indicator that is above the blue line, we will be using lots of resources that will make worsen this indicator. So what we are trying to do in the group now is to try to tackle better these to group better these two modeling tools, Calliope and EnBIOS. And for this, we need to make the assumptions of both match, because EnBIOS, Calliope makes some assumptions on how the future of the economy will look like, on how we will produce steel, for example, or what kind of vehicles will be out there. And in EnBIOS, we need to make sure that how we model the economy with our tool in the future is exactly the same as Calliope does. And to do that, we use life cycle inventories. And of course, because we are looking into the future, there is a huge challenge, because we need to get data on prospective technologies or on how technologies from today will evolve into the future. And after we have combined these two tools, our idea is to work on some value maps so we can assess different energy system options and how would they look in terms of environmental impact. And to make the results fit for purpose, we are working on 3 different case studies in Portugal, and they are focusing mainly on repowering, in Bulgaria, where they are focusing a lot on offshore wind, in the Black Sea, and Spain, where we focus in the region of Catalonia and this Parc Tramuntana. So in the case of repowering in Portugal, we've been, as I mentioned before, we've been collaborating with a company there that operates a wind farm, and this wind farm has 20 megawatts and 11 turbines, and we are trying to analyze several possible end-of-life strategies. This includes a short life extension of 10 years, changing only some parts of the turbine, a longer life extension, changing more parts of the turbine and making available for another 25 years, substitution, so taking exactly the same turbine that we have today and going to the second-hand market and placing exactly the same turbine and operate them for another 25 years, or repowering, which would be to reduce the number of turbines and place less turbines with bigger power. And of course, analyzing all of this is not easy, because if you repower, you use more materials because the turbines are bigger, but at the same time, you are able to produce way more electricity. So we need to take into consideration all these possible trade-offs to have a good comparison. And we are working on a paper right now that hopefully will be out there soon and you can check. And finally, in Catalonia, we are working on the regionalization of the impacts. So of course, when you look at life cycle impacts of a technology, you usually get one single number that doesn't tell you exactly where these impacts are happening. And one thing about the wind energy is that, of course, the manufacturing happens elsewhere, not exactly where you place the turbine. So it's mostly where you extract the materials or where you manufacture it. So we try to map different impacts in the territory, considering what impacts are happening on the site of operation and what impacts are happening elsewhere. And of course, when you look at global warming, it's clearly visible that most impacts are happening elsewhere because they are manufactured elsewhere. But when it comes to land occupation, the impacts happen mostly where you are going to install your turbines. And this is going to be more interesting when we include other technologies where you burn stuff on site, so we can better see in an entire energy system what kinds of impacts we are creating on the site of production and what kind of impacts we are creating elsewhere in the value chain. And this is all on our side. I'll be happy to answer your questions later, and here you have our contacts in case you are curious to know more about our job. Back to you, Nick.
Thank you, Miguel. That was really interesting. And the different trade-offs that you have there in terms of the environmental impact and negative impact as well in terms of the life cycle of the products and the production of the steel. So lots of different aspects and things to consider when making decisions. And very interesting, that final slide on the impact on the communities, both in terms of physical impact and then on climate impact. So thank you very much, Miguel. That was really thorough and really very, very interesting. So next up is the WENDY project. And I'm pleased to introduce Frank Hansen, Thomas Cavalnes, and Reto Spielhofer. Apologies, Thomas, I'm sure I pronounced that wrong. But over to you, and thank you very much.
Yeah, thanks a lot, Nick, and I hope you can see our screen. Hope that works. So yeah, thanks a lot, and welcome from our side, the Norwegian Institute for Nature Research. And actually, our story fits very nice in what just Miguel talked about. It's actually about impacts on very regional scale, on spatial explicit impacts, and we will explain you about two tools within the development of the WENDY project, new funded project on augmenting the acceptance of wind energy. So we talk about the ConSite tool, my colleague Frank is working on. And then we also talk about an ecosystem service and biodiversity LCA modeling tool or impact modeling tool that Thomas and I are going to present. So as you all know, the development and operation of wind energy is influenced by the natural, the social, and the technology or economic environment. That's nothing new. But now the impacts, to be in a way a holistic impact assessment tool, needs to cover all the three. So the WENDY ConSite tool tries to be spatial explicit and tries to assess all the three dimensions simultaneously. When we're gonna talk later on about the biodiversity LCA impact tool, it's mainly related to the natural environment, and the ecosystem service LCA tool is kind of at the border between the social environment and the natural environment. So these two tools are actually kind of integrated into the main WENDY ConSite tool. So first, Frank is going to give you an overview about the ConSite workflows, about the data, mainly the spatial data related to the ConSite tool. I will then briefly explain the ecosystem service part of the LCA modeling tool. And finally, Thomas is going to show about the biodiversity or the species richness LCA tool, while then Frank shows a demonstration of the ConSite tool and also shows where the ecosystem service and biodiversity comes into ConSite and how that looks like. So then I hand over the screen to my colleague Frank, just sitting next to me.
Hello, everybody. Yes, the purpose of the Concite tool, which is, I should start to say the Concite is a short form for consensus-based siting, is to provide the decision support in terms of predicting, analyzing, and visualizing scoping areas for reconciled siting of wind power plants based on social acceptance and ecological and technological trade-offs. So the tool it consists of several panels where you follow a workflow with trade-offs and special filtering, and at the end you do this siting to find suitable areas for wind power development. And then you can then also do some statistical analysis and download your results for further assessments. I will show some examples later in the presentations. The operational impact is to enable the users to balance the ecological values, or should I say the socio-ecological values when it comes to the utilitarian perspective, with the wind energy potential in the landscape or offshore in the seascape. Also to empower users to develop a targeted suitability map that incorporates relevant curtailments and also the different perspectives of holistic decision making. And then finally to effectively guide subsequent decision making processes regarding siting of wind power plants, more like sites, and then also do some preliminary micrositing of wind turbines to be further assessed in engineering tools. The workflow is, we have tried to illustrate it in this figure. The core component is the trade-off between the ecological values and the technological values in terms of the annual energy production potential. The tool is have kind of two tires when it comes to the mapping of the utilitarian values. So you have this LCA tool that Reto and Thomas will present later on, but you can also, where you can do a local mapping in a local case study, but you can also just use a European scaled ecosystem service proxy map to do an exercise just based out of proxy values. The ecological values is currently only representing the utilitarian ecosystem service values, but we will also combine them with the intrinsic values of biodiversity that Thomas will present later on. And then the idea is that you can filter out a scoping map based on the curtailment mask, that is restriction areas, and also different levels of acceptance, threshold values when it comes to social impacts, when it comes to costs of producing energy, and also this biodiversity impacts. And then the next level is where we are currently in progress of developing the kind of siting and statistical functions where you can apply different siting and optimization decision rules regarding suitability, requirements regarding installed capacity, production, net environmental performance, and so on. So you can kind of make some preliminary areas that are satisfying your requirements, and the idea then is to do some preliminary micrositing, find the top 50 pixels for optimize production, and then you can download everything and do some further and more detailed assessing in engineering tools that are on the market. So I think I leave the floor for now, and I think it's Reto, it's your turn again. Yes, thank you.
So as you see, the Consite tool, it's spatial explicit. Thus, we need maps as a basic input. And when we talk about ecosystem services, so that's kind of the utilitarian value of nature. So how do we people benefit from nature? And actually, within this task, the first exercise is to map these values. So we need to know where people benefit from nature and how much they benefit. This is very regional specific, so that's not directly possible to do all over Europe, for instance, because different values are different in many different regions. So we do that within a participatory and consensus-based way. We engage and include people, local stakeholders. Within the project, we do it, or at least we test it for 10 different services. It might come out that not all the services need to be mapped like this, but we try it for 10. And we do it within an online geo questionnaire that I will quickly go through. In the second step, we then need to perform the life cycle impact assessment, and we choose two different pathways. So the one is obvious, that's land occupation, and the other one is disturbance. As I said, that's spatial explicit, so we know in the end where is the impact to a certain, or how high is the impact at which location. And it would be, or it will be comparable to the biodiversity impact that Thomas is going to show, because we use the same kind of index, the potential disappeared fraction, in this case of ecosystem services. Let me show you about how we're going to map the ecosystem services. So we developed a tool called the GeoProspective tool, which is basically, as mentioned, a geo questionnaire. So single people, participants log into the tool. The study area, as outlined here in orange, is visible. And then people start to map areas where they, for instance, see high values in landscape for recreation. Recreation is a nice explanation for an ecosystem service. So can you show me areas for recreational values? Based on these training areas, we then going to extrapolate the values to the whole study area, so to the whole orange regional case. And we then have an individual map for recreational values. We then can overlay several participants, and we can produce a kind of a consensus map that's nothing else than the coefficient of variance, and where we have lower values of variance, we have higher consensus. So people are sure or are consensed in a way that there are high values for recreation. We do that twice. In a second round, we let people adjust their initially drawn area based on further information. So now they see where other people mapped the values in the area, and they can consider, should I adjust my polygon in order to align with the others, or do I still think no, my polygon is in the right area? We do the same routine as well. We extrapolate and calculate the coefficient of variance. The map coming out there will then be used for the LCA impact analysis. And we also calculate the mean of all the answers, which can be directly integrated into the Consite tool. the mean map represents a kind of an average value for an ecosystem service. So we then use the coefficient of variance map from the second round for a specific ecosystem service, and we go into the LCA. And as previously mentioned, we use two impact pathways for ecosystem services. The first one is the land occupation. So what do we lose by the actual foundation and the placement of the wind turbines? And for some ecosystem services, we go into a disturbance pathway. So kind of how is it influenced a bit further away than just at the spot itself. The land occupation needs then a kind of relationship between ecosystem service map or distribution and the area. So the larger the area is, the more ecosystem services we expect. And thus we need to have this spatial correlation, and we can find that out by calculating the invariability of both. And in the end, it's kind of an area lost due to the foundation of the wind turbine, which is dependent on the size of the wind turbine. For the disturbance, it's the same. We need this relationship. It's actually the same relationship between ecosystem service and area. And the area lost due to disturbance is a kind of a function of distance, of course, but also of the ecosystem service itself. So maybe recreation has other distance effects than, for instance, cultural experience of nature. So we will also assess these values in the questionnaire. We then calculate the potential fraction of ecosystem services. So how much of a single pixel with a certain ecosystem service value is lost due to land occupation or due to disturbance with this potential disappeared fraction value. And this gives us, in a way, a relative map of potentially disappeared fraction, land occupation, and disturbance. Relative means is just valid within the study area, so we can't compare different study areas in that sense. It's the highest and the lowest value in this region. And in the end, we can overlay and summarize these impact pathways, and we can feed ConSite with the cumulative potential disappeared fraction of ecosystem services, which is then used in ConSite to decide whether an area is better or worse for a wind farm or wind turbine development. I will now hand over to Thomas, who is going to talk about species richness LCA.
All right, thank you. So species richness LCA. So in this part here, we are focusing on the species that actually exist in the areas that we want to build wind farms. And we are looking at the potentially disparate fraction of species richness for any point in these maps. So sort of the area lost during the operational phase of a wind farm. So we are doing both offshore and onshore. So onshore, of course, we have both the different countries in Europe, and we work with the polygons for each of these. And within these polygons, we do our calculations. And offshore, we are working with these exclusive economic zones in Europe and do the same thing. So we are working with birds, bats, and marine mammals. Of course, birds and marine mammals offshore, and bats and birds onshore. So here are just some few example species like the minke whale, which is a baleen whale. Then we have the bats here with the northern bat, which goes furthest north in Europe. And then you have the common guillemot, which is here sitting on the sort of the ridge between offshore and onshore. So it's sort of a species that will go into both of these calculations. So the sort of overview of the LCA looks like this. So we sort of have the green part here, which is the species richness part where we make maps of species richness. And then we have the orange part here, which is sort of the impact part here. And then we have here in greenish bluish, the combination of these two is actually the LCA. So for the green part, so we are then collecting species occurrence data from GBIF, which is an open access biodiversity database. And then we use some environmental data, basically some data that are relevant for the species of concern that we have. And we can then calculate a sort of distribution map for each species and overlay all of these to have a map of species richness for any region in Europe. So here as an example is the species richness of bats in Italy, where you can see there are some high levels of species richness up here. And if you go further up here in the mountains, it gets very dark and very low number of bats that will actually go up there. Yeah. So for the sort of orange part here, first we need to identify the impact pathways, which are basically 4 different types: habitat loss, disturbance, collision, and barrier effects. And we have all 4 of them for birds, bats, and, well, seabirds, I call them here, is birds offshore. While for marine mammals, we don't have any impact of collision because there's no perceived big risk of collision for marine mammals with the offshore structures. So habitat loss, of course, is the direct loss of habitat. Disturbance is the effect that species might not want to approach an area at some distance from the turbines. Collision is the risk of colliding and being killed by the turbine, and barrier effects are then the sort of the costs of having to go around these turbine areas if you don't want to go through them. And we can see them like this, where you have the turbine positions, and then you have some area of impact, which will differ depending on the type of impact. And yeah, in behind here you see some example species richness maps where we have for each grid cell some value of species richness. And then for sort of the total thing is where we combine everything here. We're going to what is these calculations, which is really the PDF, potentially this fraction of species. I'm not going to go in detail on this equation. You can ask me if you want, but it's basically the loss of species richness for the area. This is the lost area due to building some turbine. And we then would create a similar type of a map now for Italy again, and for bats again, with a high impact areas in dark red and light red areas for less impacted areas, and this is for bats. And then you can have some histogram of these values, and you can pick some site, and you can see where am I actually in the here from really bad to really good sites. I think we'll move on here for the demo on Consite, which Frank will talk about.
Yeah, I will just leap through some examples to save some time. So the first part is you have to set up the trade-off, and then you can work with the local case studies for case study stakeholder mapping, or you can do these administrative entities at different levels, from municipality to nations. So selecting local case study, you can select your case study area and map, or you can, if you haven't started the mapping, you can interact with the geoprospective tool that Reto presented. So if you select case study area, the first thing you got, of course, is the ecosystem service map. This is just a proxy map since we haven't started with the case study areas. The next step is to calculate the annual energy production based on standard equations and the power curves for different turbine designs. These are only the turbines that we have included so far, but it could be whatever turbine design that are known. And you select the annual energy production. And the next step, you can see then how the kind of potential is distributed, and you can also see that the areas without colors are areas that are masked out because of curtailments, which is in this phase includes protected nature reserves or settlements where you should not develop wind power. Next phase is to calculate the level of cost for producing energy based on the investments and the lifetime of the expected lifetime of the wind power plants, and then based on that you can do a trade-off where you weight in a linear weighted combination. You weight ecological and the annual energy production potential against each other. You can play with different perspectives to see what are the spatial outcome of the kind of suitability map. And the next step is then to apply spatial filters for adding the thresholds of different acceptance, for example, for proximity and costs and biodiversity impacts. So you can set up different requirements, and you can also include others here as well, like inverse visibility, distance from protected areas, and so on. This is not a final list, and you can play with that to see the outcome of how the scoping areas would look like. And then, as I mentioned earlier, you have then you take these scoping areas into the siting analysis, where you do the siting and optimization, and you can download the statistics and continue the assessment in some more engineering tools regarding siting and micrositing. So this was in a rush. Please contact me if you are interested in more information, and I then will leave the floor for Reto to sum up. Thank you.
Yeah, just very quickly, since we already are a bit over time, but take-home messages. So the ConSite tool that Frank has developed, it balances the socio-ecological and economic values as a holistic tool in a spatial explicit way. And in addition, we account for these ecosystem service part, which are the utilitarian nature values. And there, with this tool, we can engage stakeholders, we can include local values and knowledge. So we are more transparent in the planning process. And adding the biodiversity LCA is the impact on the intrinsic nature value, accounting for species richness, different functional groups, and different impact pathways. So from that side, thanks a lot for your attention. In case of any questions, don't hesitate to contact us.
Thank you very much. Thank you to all of you. That was fascinating, especially the part on the species and the impact on them. And of course, the many protests you see are about the environment as well, which you always think, well, why is that? And of course, any physical structure will have an impact on the wildlife. And it's very interesting to see those different aspects in the resource that you've created. So I think possibly a question for everybody later on is how the data and how the information that is available on these tools and in this research can be applied to the right people, so that the right stakeholders are able to access the results and the information you have. But we'll come to that after the next presentation, which is from the WIMBY project. And I welcome Andrea Hamann to turn on her camera and start the presentation. I think Luis should also be joining you as well for this too. So Andrea, hi Luis, nice to meet you. And over to you, Andrea, for your presentation.
Yes, good morning. I'll be presenting some of the work from the WIMBY project. In particular, we have a lot of work going on in many areas, but for this presentation, we are focusing more on the WIMBY interactive map. And I will be first going you through some of the objectives of the project, and then talking about the data and the models behind the interactive map. And then Luis will be actually demonstrating, and we'll keep our finger crossed that everything works as we expect. But first of all, I would like to apologize a little bit, because I actually come from the totally other side of wind energy, which is the technical part. So sometimes I have trouble using all your terms that you're using, social scientists. So bear with me. I'll do my best. I've learned a lot after a year and a half of WIMBY partners, but some of the terms have not filtered in. So some of the challenges, and those have been covered already on the previous two projects, but there's a lack of understanding of the complexity of the different impacts on wind energy development. And many times communities are not aware of many of these impacts and how they relate to each other. For example, yes, wind turbines will kill birds and bats, but a transmission line will make it much more than that, and probably my cats have already caused an impact bigger than a wind turbine will. So this interplay between the different impacts is very important, and that generates local acceptance in a way. The same is with noise. People before the construction are very scared of noise, but they don't really have a sense of how it would affect them at the place they live. So having the interplay between these factors, we think, is very important. Another part that it's perhaps hasn't been mentioned so much in the other projects is that we have sometimes very restrictive regulations, and yeah, of course, Jan talked about this, about regulations in different places in Europe, but communities are often not aware of these restrictions, and for example, think, well, this was wind turbine, why are they building it here? Isn't there all this free land where it could be built instead? So what we try to do with the web interactive tool is to try to bring these things together. And the last one is, of course, the NIMBYist, as I mentioned, an example before, that many times is lack of information, or not lack of information, but lack of the ability to put the information together that creates NIMBYism. So just quickly, we are trying to put these things together in one place so that people can play around and can investigate the different impacts in a way together, and at the same time also get the benefits of the wind farm and see how much energy will be produced by this and how much, for example, CO2 will be displaced. So a little bit on the technical side, we have at DTU, we had many different previous projects where we developed a lot of data and models, but until WIMBY, a lot of them had not been put together. So we have, for example, data on the wind climate coming from a project called the New European Wind Atlas. Before, we had data on turbulence and, for example, siting of wind farms. We had other data that is needed for the models, but at the same time, then we have this, what we call top farm, which is the the code that does the optimization of the layout of the wind farm. And then models like the cost and the noise, all these models were laying around, but you had to manually do the connection between them. And now this, the WIMBY tool has the power of do these calculations as you or as the user selects an area on a map. So a little bit, this is the European Wind Atlas. This is a site where you only get the wind resources. You don't get any of the other parameters. So part of the objective of WIMBY was to bring the wind resources. Of course, it makes no sense to build a wind park if there is no wind. So the base of a very accurate wind resource is very important to the rest of the calculations. And you will see that next, later on when we do the demonstration, that the layout of the wind farm, it's of course very dependent on the available wind resources. So let me guide you through what is the WIMBY interactive tool, and Luis will demonstrate later, but you have an input, you choose a polygon on a map of Europe, and then you can select your number of turbines and the type of turbines that you want to install in this polygon. Then there is turbines restrictions, of course, and then there is exclusion zones that are gathered. So on the fly, we determine in this polygon which of the area could actually be built. And we know that if you already have a road or you have a house or you have something, you cannot build a turbine on top of it. So those things are taken into account. Then the wind resource is gathered. And then there is a feasibility check. If you cannot build anything, then the area is not feasible, and then you have to recreate a polygon. Now, if the feasibility check is there, then the area is feasible. You create a new layout, and then you make a resource calculation. And by the way, the layout design does consider wakes. So it's not only placing the turbines at the place where there's the most resource, but trying to minimize the wake effect between one turbine and another. And I'll show you how that is done in a minute. So the output then is the annual energy production, or the capacity factor, the load hours of your wind turbine. And then out of this calculation, then a lot of other models are triggered. At the moment, we only have the energy production, the noise, and the LCA, and the flicker of the wind turbines. Sorry, that is an old slide. I should have done that. But anyway, some of the inclusion zones that are included are, for example, the slope of the terrain, the buildings and urban areas, the thermal footprints. Then out of OpenStreetMap, there is a whole series of different things in the landscape where you, of course, cannot build. You cannot build in rivers, inland waters, and then we have a whole selection of protected areas. Over offshore, there is another set of restrictions. These are at the moment not visible on the map, but soon they will become available, because we think that's a very important information for a person that's using the tool to know, what areas is possible to build or not. But here's an example. For example, this is southern Sweden, and you can see that many areas now will be included. The yellow areas here are the ships that traverse, and this is given by the density of ships. Then you have the red areas that are protected areas. The green ones are sloped. If the terrain is too sloped, then you cannot build. And then there are urban areas, for example, here, where it wouldn't be possible. So we anticipate that the website will look something like this in the future, but it's not yet. That is coming in the last version. Then, for example, I'll give you through an example of the optimization. So this is actually the Riso campus where DTU Wind Energy lives, and we're somewhere out here. So this is an area around our campus. The area to the left is actually the fjord, the Roskilde fjord, so that is eliminated. And then there are many areas also where are excluded. Many of them are nature protected areas. So what happens when we, of course the optimization doesn't work. It didn't run. Well, let me guide you through how this works. But the optimization of the wind farm is done in what we call a smart start algorithm. So the first time that you run this was an animation, but you will get the location where you can get the most power, which is here, for example, in this label, gives you the annual energy production. So this is the first turbine. And then a second point will be chosen for the next energy production. Now wake is active, so some of the areas, the whole energy production of all the other points will be recalculated after each step. This is quite quick at the beginning, but once you have too many turbines, you don't have the ability to move the first one in the first place. So after that, we use, there we are. Okay, so that's going through that selection of these points, and you can see how the resource is being changed as you locate these turbines. Right. Okay, so after the first iteration, then you use a stochastic gradient descent to further move the turbines so that they are in an optimal place. And this is how this would look like. So each of them using the gradient then adjust the position of the already selected turbines. But you will say, well, why bother with all of this? Well, this is being done on the fly. So the main constraint here is time. Of course, if we had, 10 minutes, we could find the optimal location using many different algorithms. But the idea is that the calculation should at the most take about 30 seconds, that we know that as the maximum time that a user would spend on the website. Otherwise, they would just, lose interest. So there is a constraint, there is you need to trade off between the time needed for optimization and the energy production of your polygon. And some of the colleagues at TCU have worked on that the best way can be done first with this smart start and then with the steep descent algorithm. But let me show you some of the other models that are coupled. So this is again the map that you had seen before. So out of this output, then there is a noise calculation that is done for the same wind turbines and the wind speed at each of the sites. And Luis will hopefully demonstrate how this works when you choose an area. Then we also have a shadow flicker model that will be overlaid on the turbines that you place. At the moment, this one doesn't take into account the terrain. The variations in the terrain is considering the site as flat, but in the next iteration of this model, that will be also considered. And the third model that's included is a live assessment of the turbines, and that has been spoken before by the other two presentations, but you get an estimate of the life site assessment of the turbines that you just built in your when you did the calculation. But now it's time for Luis to go through, and I'll stop the share so he can come in.
Yeah. So hello everyone, Luis Ramirez here. I hope you can hear me properly. Yes, correct. Great. I just need the right to share my screen by the organizer, and then.
I thought you had it.
No, The sharing is deactivated by the...
Yes, let me see. Okay,
My
now.
words. Great. Yes, perfect. Thank you. So, well, basically, I'm representing to you the entire back end of the tool. I'm just showing you here the landing page of the current version 1 of our interactive map. And for now, it's just informative. So it gives you the information on what you can do. That is, create your own wind farm simulation, consult a layer on the map, or discover the pilot sites in the WIMBY project. And I will start with consulting layers in a map. So as you saw before, we also have data that has been extended from the new European wind atlas, as for instance, the wind speed. You will get, well, for the entire continent, the information. You can get it in 100 meters height or in 200 meters height. In a high level of detail. The same goes for the power density. You can also select the altitude of that you want to know between 100 and 200 meters, and you will see it in the map. We also have on our layers related, for instance, to elevation, and something that is critical also for the planning of wind farms is the roughness index of a particular location. What we also have here is our pilot sites. So we have pilot sites in Norway, in Austria, in Portugal, and in Italy. And when you go, zoom in, click in there, you get some additional information here on the left. This is going to be populated for version 2. But in general, you will get information about the challenges, the possibilities, and we also want to link here what has happened with the workshops that we have been conducting and we are going to conduct in the framework of the project. So this, I will say, are the easy things. I mean, it's a great job what Nazca has done with this, and I couldn't do it myself. But I think the most interesting feature of the tool is the opportunity to start a wind farm simulation. So I don't know if the public can speak, but if someone can give me a location in Europe that they would like to have a look, I could just zoom in. I will wait 10 seconds. If I don't hear anything, I just randomly go somewhere. Okay, so I will just go to the
Valencia.
Valencia. You have to tell me when is that in the map of Spain. Valencia, there is here. Let's go. Well, as you saw, there is a bunch of hard constraints. So we are not building up where we already have some urban infrastructure or very large infrastructure such as highways. So this is really at the moment a search in the blind because the hard constraints are not visible. So I'm going to try 2 times. If it doesn't work, I jump into a pre-calculated site that I have, but let's give it a try. So we zoom in until this button turns green. And when we click on it, we have the possibility to draw a polygon. And this polygon for the moment is allowed to be up to 10 kilometers big to keep the calculation below 1 minute. I will put, I don't know, 5 turbines here. I will select a turbine type. We have 4 turbine types for the moment: onshore low wind, offshore 10 megawatts, and large offshore with 50 megawatts. Obviously, we have to select in this case an onshore turbine, and I would just let it run. So we have to wait for a bit. As you saw, this is a very optimized algorithm to look for the places with the highest production while minimizing the wake. So we are not optimizing here for costs. It's something that we want to include in the next versions of the map that are going to come out in the next months, but it's not there yet. So as you saw from the presentation of Andrea, we are optimizing here for availability of resources and while minimizing the wake. We got the message that I didn't want to see here, and it's basically there is no suitable place to place turbines in here. It might be related to protected areas, to infrastructure that is in the background. As you see here, there is an urban area. I will give it another try, close by, maybe more towards the countrysides. This is already quite big. Remember, we have to stay between the 10 kilometers. Now we have the 10 kilometers. Let's try with 3 turbines, so it solves also quicker. It always varies from time to time when you're demonstrating this works perfectly. It's still in a test stage, so this is not production. This link that you see, I will ask you to please not try that in your own yet. We will be distributing the operational and debugged versions as soon as we have it. It worked this time, and as Andrea told you, well, we have here the first output that we have on these 3 turbines is the total energy output, the capacity factor that is there, and you have also some regulation warning. What means this regulation warning in this case? If we don't have further information for the location, as it is in Spain, because it's not a WIMBY country, we just showed you the additional regulation that that you can find at the European level, like the minimum restrictions that you will find while positioning wind turbines. And if the information is available as from WIMBY countries, you will see the regulation that really applies to that particular place. If you want to check if this was really the places with the highest wind, you can also have a look of the power density map in the background. And you see there, for this kind of turbines, you see that the highest values are here under this line, and it's precisely there where the turbines are located. And then we go to the impacts, and we have the noise impact. So we have the online calculation of how many decibels are around each one of the turbines. And we have also the shadow flicker calculation. I will try to move the window here, but you also have, for instance, a 3D visualization of this for each one of the turbines. We are working on how to better present this kind of information, because at the moment it looks like it's very shadowy all around the turbines, but in the end it says that it's up to 150 hours, but that probably only happens for 1 or 2 pixels in what we're presenting. So we're definitely working on how to present this better. And the last of the impacts that is already implemented is the impact on amount of emissions per gigawatt hour produced that goes from cradle to grave. We also have other functionalities in the tool. We can also leave our feedback if we find any bug, or if we want to say, great tool, we would like to use it for our projects. And then we also have a search function for locating, well, if I will type Valencia, we will go back there. Comunidad de Valencia, so that will have helped me to find a place if I was not aware of where is it located. And yeah, well, basically this is version 1. We have another 40 months now to continue working on this. We expect to have additional versions that introduce more impacts or more results from the WIMBY project. Eventually also some results from the JustWind4All project, and also better functionality. We also want to have a game. And I don't know, Rebecca, if this is also going to be presented today, but we also have a forum where people will be able to exchange and share the project they are working on. And I think
Luis,
yes.
If I can, there's a question from Marta Rimada, who's asking if you could try an offshore location in Spain too.
Yes. Let me just restart here. Also in Spain, let's see what happens, because you also saw the restrictions that are applying there. I have to zoom in until I get the 10 kilometers. This is already quite big, so I mean, I'm just making a random polygon, right? You will be able to upload whatever polygon you want, and we're also going to offer an API. So this is at the moment just for demonstration. Let's put, I don't know, 6 turbines. Let's select some large ones, and we will see. In general, the amount of restrictions that we have implemented for offshore are less than we have for onshore, and we don't have any mechanism yet to differentiate between floating and ground-mounted turbines. So that's something that we are working on, but it's definitely not available in this version yet. Yeah, something is happening here. For the next version, we also are going to show the restricted areas, the exclusion zones. But yeah, well, I don't know how are we with the time. I can also give it another try, but I wonder how are we with the time, Nicolas? I don't know. You tell me. Should I try again with the chances?
Yeah, you can try. Yeah, if you like. Yeah.
Okay.
We've got 20 minutes, so it's fine.
Second attempt, but it's, let's see. And so big, make it smaller. 11, I have to make it even smaller. Got too big. Now, good. Offshore 15, and then run. And it already identified a major restriction there, so probably the entire area is blocked.
There's this suggestion from one of the participants to try the Portuguese Atlantic coast.
I tried last time with one of our case studies. Maybe that might work, but well, let's go for Portugal. All good. We're already quite far away.
Yeah, don't go too offshore because it's gonna.
It's not going to find
the depth? Don't
yes.
think so.
Let me go back. All right. Final try. Now there we are. Again, big. Try with more turbines, big ones, and then run. Yeah, unfortunately, I don't know very good how to, I don't know the shipping lines that well. So I hope I didn't cross any of them. Let's see. Well, we have some results here. Let's check at least the power density. Is very homogeneous in the entire area. So probably we were just minimizing wake in there. And yeah, what you also will see here is that the impacts are still calculating. So we have this image here for calculating, because the moment the turbines are selected, we start calculating on the fly the noise impact. And the shadow flicker also takes like another 40 seconds maybe, because it's 8 turbines. Yes, it takes a little bit of time to calculate. Everything is calculated on the fly. So I hope I'm not seeing the chat. Yes, Portuguese. I see now from Rebecca the answer. Well, Nicolas, the question for me would be if we have a lot of questions from the public, we should go ahead with it. Otherwise,
yeah, you can. Yeah,
there is some content from Rebecca on the forum, but in general, there is a forum for exchange. Very nice. The visuals are very nice, and the idea is really to construct these projects and be able to share them, comment about them there. That's the idea of
Great stuff. Thank you very much, Luis. I think
Mhm.
the turbine start. I think the results have just come in. You can. But if I can ask the other presenters to turn on their cameras, and we just have a little time for some questions. There's a question actually specifically to Miguel. From Rebecca Huting. Sorry for my pronunciation. So first of all, thank you for the presentations. We'll go to Rebecca's question first, and then if there's no further questions, I have a couple of questions as well for you all, because they're all excellent presentations and really interesting data, I think, that it clearly could make an impact in evidence-based decision making. So the first question comes from Rebecca Huting, which is specifically to Miguel, and she asks regarding the CO2 impact of turbines. Are you considering the actual amount of recycled steel used for turbine production, assuming that it's all sourced from Europe, or are you forecasting the use of 100% locally sourced steel? I guess there may be manufacturers which use steel which originates from other countries, such as China, where recycled steel and RES rates in the energy mix are different. So that's a question to Miguel.
Yeah, thanks for the question. So at the moment, we have, like, when you input your parameters to the modeling tool, there is by default you have European steel with the amount of recycled steel as today, like as last year actually, but you can tune that. So if you are trying to model a turbine in the future and you have a projection of how the industry will look like by then, you can change the amount of recycled steel manually, and you can introduce your number, and you can also change the electricity mix that you are willing to use for that calculation. But by default, you have the current situation, and we are always assuming it's European steel.
Okay, thanks, Miguel. Thank you. Yeah, clearly the project's focus on the EU landscape, and my next question is about that. So you've all of your, and also Jan as well, the study that your team has, your colleague and yourself had created with regarding the visibility, the visible impact. And so my question is, they've got a load of fascinating data. The projects have all, as regards the call that you all responded to, is to create tools which can be used by different people. So I say people because, of course, you've presented different types of data which are going to be interesting for different types of people. And my question is how can you ensure that the right people get use of your tools, because they're all really excellent and really provide great insights. They also give a lot of flexibility to the user to use the tools. And one of the things which Andrea mentioned was the time, the time that a user has before they lose interest, which is very important. So how are your projects, and also Jan, how's your team ensuring that the right people who get the right access to the right data and are able to use your tools effectively? So perhaps we could go first to Jan on this, and we could go in the order of the presentations. You've got about a minute, sure. 2 minutes to answer.
Yeah, I mean, we didn't really have a tool or a web page like Luis presented for local stakeholders to play around. I think in our case, it's more directed to national stakeholders. And then, I mean, we usually have these scientific publications, but I think it's rarely that these national decision makers will read them. but we also from our institute have some press conferences with press and also politicians in Berlin, where we present our scenarios. And I think this could be a good way. In general, I think our results are relevant for these national stakeholders, because when we think about local stakeholders, then there's much uncertainty in the data of scenicness and how the people perceive it themselves who live close by. And yeah.
Yeah, thank you. Yeah, so national decision makers are key there, and getting the information to them is important. I suppose the name of your institute is important here as well. It can be influential. Okay, so I'll ask Miguel that question as well, just for.
Yeah, so in the project we have our package that is all about wind labs, and there are, I think it's 4 wind labs, one in Portugal, one in Bulgaria, one in the Northern Sea, and the other one is in Germany for airborne. And the idea is that we use the information that we provide with our tools to make it use in the workshops that they organize in these wind labs, so they reach the appropriate stakeholders in their particular environment, so they can help the actual people who is working in the real condition settings to take the decisions. And so far we held a few already of these workshops, one in Catalonia, for example, where we also presented different ways of showing the results that we have, so they could give us insights on whether this way of presenting things are clear enough, or they create confusion, or how to improve that. So that's something that we are trying to work on also.
Excellent, thank you. Frank and Co.
Yeah, exactly. So it's a really good question. Within the project, it's similar to just WIN4All project. We also have in the WENDY project these stakeholder events. We have a network of interest. So if you are interested in, you can just sign up for this one. And so within these stakeholder events, we can promote the tool to the accurate stakeholders, but we also might find out what will be the right people, which will be the right decision makers within these events, so that hopefully also comes out of the project. But that's of course in the end, when we're gonna finalize the tool, we need to define that more clearly. Yeah, so it's not defined yet, but I think especially ComSite will be more on a regional scale. So national regional authorities that already have in mind a strategic plan can apply it. Yeah. Do you want to add something, Frank?
It's more like also the use of the tool in previous projects. It has been kind of linked to the processes that are run by ordinary impact assessments. Let's say we have tested it for power line projects where the Directorate of Freshwater and Energy has kind of identified the relevant stakeholders from this power interest assessments of who is kind of influenced and what are the different roles. So I think that could be the context for the original use of ComSite.
Great, thank you. And then to Luis and Andrea.
Maybe one thing that was not presented here, and maybe might look, but I mean, something that is here from what we have presented is we already spent 1 year of process of identifying audiences and the way these audiences might use the tool. So I think that's very important. And from the target audiences that we have in the project, we have basically interested audiences that are like communities or people around potential projects or simply interested in wind. We have expert users, scientists, people from transmission operators, or even planners of wind turbines, and also education. And for each one of them, there is basically a different channel for education. We're trying obviously to promote the use of the tool in our classrooms. For the experts, well, we have the network, so events like this might help to bring it out there. And then for the interested audiences, well, we also have our pilot regions where we run workshop weeks to present that we have the tool and could be useful, but we also live a little bit on the word to word. This is snowball principle of trying to, well, we're quite convinced that our work could be helpful to understand better wind power and wind power impacts. So any chance that we have to talk to anyone, even if it's just a friend or the teachers from the school of your children, we let them know about it. And in the way we think we're reaching people, and for each one of them you will have basically different functionalities in the tool. What you saw now is just bringing everything together and see how it works together. Well, not everything, because not everything is there yet, but we wanted to show that it works. But now the work that is going to happen in the next months is also about how to make it useful for each one of these three target audiences. That's the
great. Thank you. Yeah. Okay, yeah, so I think we've got time maybe for a minute answer each, because one of the things which Miguel mentioned was the future. Well, you all mentioned the future really, because your tools provide the opportunity for people to explore new things. And Miguel mentioned new technologies as well, and emerging technologies which could change the way that the future of wind energy and improving recycling of steel. So looking at that, I've just got a question to end. Okay, so in the future, how do you see the future of wind power and wind energy, and the importance of the interaction with communities and different stakeholders? So let's say 5 years' time, how do you see the situation? And this time, let's go backwards. So I'll put this. Sorry, putting you on the spot, but if you've got a minute to say how you see the future, what are the key things for the future? So Louise and Andrea.
Andrea, did you want to take this one, or should I tell me? No? All right. How I see things, I think wind power is a proven technology. Yeah, and we well, obviously we need to communicate better how it works. We need to reach better agreements and where to put it and where not to put it. But I think the future should be just full of wind. We don't need the big discoveries to make this happen. But we have the technology already. Yeah, obviously there are developments in floating. There are attempts to have airborne winds and everything. But for me, the future is basically now the technology is there with these tools that we are providing. We just hope that there is more adoption of wind power. And that's my 30
thank you. Thank you, Luis. Okay, Frank, Thomas, and Reto, do one of you want to take this 1 minute?
It was a very interesting question. I think how we consider is that the local regional scale is more and more important, and to kind of these tools are important to kind of establish a common knowledge platform which is transparent and which is kind of also helps to identify the different interests and their values, and to kind of, it will also make it more like the stakeholders may be more committed when they perform a mapping and the values are on the map. So I think the tools should help to guide the process better in the future. So this, I hope.
Thanks. Yes, exactly. We do hope. Yeah, thanks, Frank. Okay, and Miguel, to you.
Yeah, I would say that there's definitely a need to involve like local stakeholders for sure. So And here I mean not only like financial participation, but also like having a real say on how wind parks can be designed. If they are going to be next to your door, you might want to have a say on how to design everything. And for this, there need to be opportunities for discussion for these people and having a say. And also on a more general level, I think that there needs to be other discussions in terms of justice, like communities are affected here, but also somewhere else where we are extracting resources. So we need to discuss more in depth that it's not only about us, but it's also about lots of communities elsewhere. So it's a very complex problem that should be more out there, discuss everyone and discussing it. So yeah, that's how I see it. Maybe too personal, but
that's fine. Personal is important, Muriel. Thank you very much. And to you, Jan, over to you.
Yeah, thank you. Yeah, first of all, I agree with all the opinions before, and as Luis also mentioned, I think wind power is a very important and large part of future energy systems. That all energy scenarios show this, and I think there are some countries like Germany, for example, where it's forced now to have 2% of the federal state area for wind power, and if we yeah, remember the map that Andrea showed for Germany, where all the wind farms were in the north. Now Bavaria also has to increase the amount of wind plants, and I think all these three projects are very important now for all the local stakeholders, because they have to install wind power and now can use these tools to maybe identify sites with the lowest impacts.
Thank you, Jan, and thank you to all of our speakers today, and thank you everyone for attending. I think this has been really interesting to understand the various trade-offs and interplay between the various impacts, both positive, and to help people understand the impact that these renewable energy sources can have on their community, both positive and both negative, so that they can investigate and understand better and make evidence-based decisions, which I think this is all about. And I think it was very interesting also to hear the multidisciplinary aspects of all of the presentations, where different aspects have been taken into consideration regarding materials, visual aspects, size, and wildlife, and also the important point on regulations. So thank you very much, everybody. The recording of today's webinar will be available shortly, as well as all of the presentations. So once again, thank you to all our presenters, and thank you to the people who have stayed with us this morning. Thank you very much, everybody.
Thank you.
Thank you. Bye.
Thank you very much.
Bye bye.
bye bye. See you.
Bye.